consider an application of the material derivative of particular relevance to the derivation of the Bernoulli equation. And that's the material derivative of acceleration. Traditionally, we write acceleration as the time derivative dv dt. So acceleration tells us how does our velocity change as a function of time. But here we can now distinguish between two different accelerations. We can look at the Eulerian coordinate system, where we look at the acceleration of the fluid at one particular point in time and space. And we can also look at the Lagrangian acceleration, and the Lagrangian acceleration tells us how does a particular fluid particle accelerate as a function of time as it passes through the fluid. And so we can express the material derivative now for velocities, and it relates the Lagrangian acceleration along a streamline, in this case ds, to the Eulerian acceleration. And the special case now is the following. When our Eulerian acceleration is 0, meaning we have a steady state, system, so we have a steady state fluid flow problem, so the Eulerian acceleration is equal to 0. That does not necessarily mean that the Lagrangian acceleration is equal to 0, because as our fluid passes through, or as a particle passes through the fluid, that individual particle can still change velocity even though the fluid at a specific location remains steady without velocity changes.